We are very happy to have Professor Tadashi Takayanagi from Yuka Institute of Theoretical Physics, Kyoto University. And Tadashi is one of the leading expert in the field of holography and AdS CFT correspondence. He works in the field of quantum information theory and holography. And he is the proponent of so-called Ryu-Takayanagi Formula, which compute entanglement entropy in AdS CFT, which actually has changed the game in the past few years. So we welcome Tadashi, and we are glad that he is able to give us a colloquium. And we now hand over to Tadashi actually to start the colloquium. So one more thing is that before we start, I request everybody to ask questions at the end of the colloquium. So just not to distract it. Okay, so Tadashi can start.
Thank you very much for very kind introduction. It's a great honor for me to give a colloquium in IIT Gandhinagar. Thank you very much for Arpan. Thank you very much for kind invitation. It's a great honor. So in this colloquium, I'd like to talk about the recent idea of some emergent spacetime or emergent gravitational spacetime or universe from quantum entanglement, especially in the context of holography or AdS CFT correspondence. So let me begin with quite a basic point of the scientific research. Okay, sorry. Somehow I cannot. Sorry, somehow I cannot change page actually suddenly. Maybe let me do this again. Okay, it works. So, introduction, and as you know, in scientific researches, microscope, some sort of microscope plays very important role. It's a basic, very important experimental device. And in biology and chemistry, and also condensed matter physics, we use microscopes, like optical microscope, electric one, or X-rays to magnify some basic constituents like atoms or molecules and so on, or cells. And in particle physics and nuclear physics, we use a much larger version of microscope, namely accelerator, to get a much more large scale magnifications, a big scale of accelerator like LHC or much smaller accelerators. But I'm working on string theory or some quantum gravity, which aimed for unification forces and also most fundamental laws in nature to understand some basic physics. And that case, actually, so we want a higher magnification in some sense. And that case, even though this is not real experiment, but this is a thought experiment, but a very useful device for this microscopes is holography, is called holography. This is not exactly the same as the optical holography, which we can show here, but it's much more gravitational holography. I will discuss the detail later. This is especially in the light of AdS CFT correspondence. And so, because I just mentioned string theory, so this is a very brief summary of this, what is string theory. So this is aimed for the most fundamental theory. But string theory assumes, starting from the assumption that the most minimum constituent of matter, basic constituent is strings, not particles. Of course, particle physics based on elementary particles, but string theory starts from strings. And this allows us to unify all forces. And in the end, leads to the theory of expected to lead to the theory of quantum gravity. And so strings consist of the two basic ingredients and open string. So there are two kinds of strings. Open string has two endpoints. It's just cut. You have a rope and we just cut into two halves. That case, we have some endpoints. And another one is just a closed loop, right? Closed loop, just the endpoints are connected, closed string. So there are only two kinds. But the point is that these two strings consist of same thing, same material in some same string. So they are actually equivalent in some. And open string, we have endpoints. We can put some charge there. So that allows us to describe electromagnetism or a strong weak forces like QCD or nuclear forces. And that comes from open string. On the other hand, closed string is like this kind of closed rope. It's a closed ring. So actually, there are two propagating modes, left moving and right moving, right? This way or this way. So that means actually in the end up with spin 2 particle. Spin 1 is a gauge field, like a Maxwell field, but spin 2 means gravity. So we get the gravity. But as I mentioned, these two guys actually consist of exactly same material in some sense, same string. So they actually in the end turned out to be unified and somehow equivalent. This plays a very important role to understand the idea of holography and also how string theory describes spacetime. So this is a very, very brief introduction of string theory. But in my talk, strings not always play a very important role, but in the end outcome is very important role, namely holography. So anyways, so if we think about the string theory, so we say the holography is a nice microscope, but then we should think of what we magnify. Right? In particular, we magnify elementary particles or some nucleus and so on, right? Molecule and so on. But one of the most interesting and the simplest targets for string theory, but here I mean thought experiment, not real experiment, but in thought experiment, most interesting target is black holes. And we want to generalize illustration. So we also want to magnify more general space-time, such as anti-de Sitter space. This plays very important role, or more realistically, de Sitter spaces, or more. If we wanted to know the origin of our universe, we should understand the Big Bang universe and magnify Big Bang singularity. And in general relativity, it looks like singularity, but string theory basically expect that in string theory, we expect that usually such a singularity is resolved. But to see this, we need a magnification. And the main question of this colloquium, which I would like to talk about here, is what do we find if we magnify such a gravitational space-time? What do we do? What do we see by using the holography as a microscope? And in the end, this is heavily connected to the idea of quantum information. We see in the end some sort of quantum information. So this is the main message. Okay, so these are just a brief introduction, and I'd like to go into the main topic of this colloquium. So first, start with black holes, and I'd like to explain the black hole has an entropy inside, and then switch to a little bit different topic, but actually they are deeply connected, namely quantum entanglement. So this actually, you can regard quantum entanglement as some microscopic counterpart of black holes. And then we unify these two ideas and then going to the holography and its connection to entanglement. And finally, go to the main topic of this colloquium, that's how we understand emergent universe from quantum entanglement. Okay, so let me go to the black holes and entropy. As you know, black holes is an extremely dense astronomical object, even we can see in our universe. And it is too heavy for particles, and it's too heavy that its strong, very strong gravitational force prevents particles or radiation going out of the black hole. So outside observer cannot see inside, so it looks like black inside. So that's the reason we call it black holes. And in a astronomical observation, so we can see that black holes are formed via gravitational cracks of heavy stars. So in the end, they squeeze to zero, very small size, and makes a black hole. And in a general, this is a summary of general relativity textbook about black holes, but just, very elementary way. And so most typical, most famous example of black hole, simplest example is a Schwarzschild black hole. And it's described by, in general relativity, we describe the background by metric, gravitational physics by using metric. So this is a time component, and this is a space component, and the spherical component. So the point is that, so we have a very simple equation and very few parameters. M is the mass of black hole, and Gn, Newton constant, is just gravitational constant. R is a radial direction, so it's roughly the distance from the black hole. It's like a coordinate in this black hole, from black hole. And so the point is that, so we have a time component, 1 minus R over G, 2G Gn. This vanishes when R equal to 2Gn M. It's proportional to mass. So at this point, we call this the black hole horizon. And outside of that, it's just sort of regular space-time, but inside that is really black hole, and we cannot see the signal from inside of black hole or outside observer. Outside observer cannot see inside black hole because it takes infinite time until the information reaches to the observer. It's impossible. And the region surrounded by this RS, this is called Schwarzschild radius. That's the radius of black hole. This internal region is a black hole. And this Schwarzschild black hole solution background is obtained from this, as you know, like it's come from the Einstein equation by solving Einstein equation. And the Einstein equation, so it's come from the idea of general relativity. Space-time is get curved due to some massive object. So we have some mass of black hole. This gives them energy or matter. Existence of matter means we have energy. And this Einstein equation equal to curvature. So if we have some massive objects, then that changes the geometry of the space-time. So this is, and the general relativity tells us there is such a solution called black holes. And naively, mathematically, this is just some equation, but this includes a lot of deep physics. It's also even includes a lot of paradox, which is very important to understand this topic, this recent progress also. And so I'd like to talk first, I'd like to note that black hole has entropy. So here is a very kind of cartoon that we start from some start, maybe sometime binary star. So we have a star, and outside observer, of course, can see the star is a very light, a lot of lights from stars. They are shining, we can see that. And a lot of information can be accessed to the outside observer. But once they collapse and the distance gets closer, and once black hole home, this outside observer cannot see inside the black hole. So this original information, which is like how many atoms or how many electrons are there in the stars, how many and so on, how many particles and so on, and that kind of detailed information is gone after black hole home. Only charges, or angular momentum can be observed outside of it. So that means there are very huge hidden information inside the black hole. So then it's quite good. So basic physics question is that we want to some quantity. We want some quantity to characterize this information. So we want to estimate how the amount of information hidden inside the black hole. And this leads to the idea of black hole entropy. So black hole has an entropy, hidden information. So in physics, we measure the amount of unsuccessful or hidden information by entropy. So this is a quite familiar formula, S equals log W. W is the number of microstates. Just log of this microstate, number of microstates. But more generally, so this is also important for, this formula is quite important for my talk. And it's like we can more advanced formula, advanced description of entropy, namely in terms of density matrix. So density matrix gives a probability distribution, and it's minus rho log rho. This is the definition of von Neumann entropy. And this is a more general statement. If we have some generic probability description, now this is a quantum version of what is known in classical information theory, namely Shannon entropy. It's a P log P, sum of P log P. P is a probability. Okay, so this is a black hole entropy, and the black entropy has a very beautiful formula. It's a very famous formula, which is also very basics of this my colloquium, and also based on a lot of this progress of string theory and also theoretical physics are based on this formula. This is called Bekenstein-Hawking formula. So founded by Bekenstein-Hawking. It's quite long ago, more than 40 years ago. But even though this is found in 40 years, or more than 40, 45 or like such a quite long ago, but this formula itself, interpretation of this formula, there are many interpretations, many explanations, but still the real essence of this formula is still mysterious. So that motivates us to study actually this topic, even today. And so anyway, calculation of general relativity, this is some classical theory, right, of gravity. It shows that black hole has the following entropy, very huge entropy actually. And this is also formula looks very simple, but very beautifully includes all important constants in physics, in physics. So it's like KB is, of course, entropy has a Boltzmann constant, this statistical mechanics. H bar is a Planck constant, that means quantum mechanics to understand this formula, even though origin of this formula originally come from the classical theory of gravity. And Newton constant G nu, of course, gravity. And finally, also this A is so entropy, this formula says that entropy is proportional to the body, not volume, but area of the black hole. And area is obviously related, come from geometry. So we have to understand, we have to combine geometry, gravity, quantum mechanics, statistical mechanics, or some this is also closely related to quantum information to understand the physics, microscopic physics of gravity, like namely quantum gravity. And also, black hole has an entropy means that black hole is a thermal object, thermodynamic. We have some black hole thermodynamics. That black hole has also temperature, is called Hawking temperature because it radiates actually. It's not exactly black, but it's like there are some quantum effect, quantum tunneling effect, it gives some radiation from black hole. And that way, energy also, we have energy or mass of black hole so that we can define black hole thermodynamics. But this is very mysterious because they originally come from classical gravitational theory. This classical gravity predicts something quantum. So this is a main reason why this formula looks mysterious. And I would like to give some nice interpretation of this formula in the course of my talk. But I should say it's not exactly completely understood. But we have a lot of interesting progress of this formula. And the black hole, but anyway, the shocking news here is that black hole entropy is not proportional to volume. Usually in thermodynamics, we learn that entropy is an extensive quantity. It should be proportional to volume, but here it's proportional to area. It's very unusual. So this proves very important to lead to the idea of holography. I will come back later. But anyway, now let me some temporary leave from black holes, and we'd like to turn to a microscopic counterpart of black holes. That's I'll explain. But anyway, we just go to the quantum mechanics. Forget about general relativity. We just go to quantum mechanics. And so I'd like to explain the concept of quantum entanglement here. And in quantum mechanics, a particle can be also have a property of waves, right? By wave-particle duality. So, and because of this wave property, we can take a linear combination or superposition of two different quantum states. So here I have the basic example of spin, like qubit spin. Spins up or down, spin half. Like you can imagine some electron spin. So this is up spin and down spin, and we can take a linear combination, orbital linear combination, and we just normalize their magnitude to 1. And because we can take a summation because these are basically come from wave function, some waves. And in quantum mechanics, we can have a state with 50% up spin and 50% down spin as a fundamental state. Even classical theory, we can have such a mixture, but that is kind of mixed situation. It's a kind of just probability distribution. But here, it's really as a fundamental state, it is called also a pure state. As a pure state, we have such a mixture of two possibilities. So this is a basic, very important point, basics of quantum mechanics as we learn in undergraduate course. And but the things are more interesting if we have a multiple degree of freedom, like two spins, more than two spins. Let's take two electron spins. One is A, another one is B. There are two electrons spin, A and B. And I will give some two basic examples. First one is trivial example. So that is a classical state, namely direct product state. A spins always up, and the second spin is always down. So in that case, there are no correlation at all between A and B. And this is a kind of classical state. We call it classical state. It's just same as classical physics. And there's also important point is measurement. We measure A spin, but this measurement does not affect the consequence of measurement of B, right? Even if we assume this state. Even though we know this full state, so we already know that both spins are up and down. So the measurement of spin don't tell us anything. But the situation changes if we think about this linear combination state. This is namely singlet state of spin if we put minus sign, or plus signs are also equivalent in quantum information sense. This is actually called Bell state or EPR state. EPR is a EPR paradox, appeared in the context of EPR paradox, Einstein, Podolsky, and Rosen, quite long ago. And this is also, in the end, this gives a highly entangled, actually maximally entangled state. So this is called maximally entangled state. And this is a two spins, a 2 qubit maximally entangled state. And here it's a very important situation is that if we measure, so let's assume we know this state. We know this state, but even though we know this state, we cannot tell A spins up or down, right? They are mixed. But if we measure the first spin, A spins up, then immediately we know second spins down because we know this state. So this pure state has such a very strong connection between the information between A and B. We say it's A and B are very strongly quantum mechanically correlated. And this quantum mechanical correlation is called quantum entanglement. This only happens in quantum mechanics. And so this leads to, so this means that if we can separate A and B in a far apart, right? So it's a very distant. Observer can share such a quantum entanglement. So this really is a kind of leads to non-local correlation, but this is not. So this doesn't breaks any, basic physics law like causality and so on. This is originally it's called paradox, but it's in the end we understand this is quite a regular, normal procedure, and this is even experimentally recently also just measured also this effect. So this is the basics of quantum mechanics, how quantum mechanics behaves. This is a very important, very basic example to understand this, and this includes the essence of this quantum entanglement. And so, but we want to, in the end, go to quantum field theory, like a very complicated quantum many-body system. So for that, we want to somehow characterize. We want some quantitative, some characterization of quantum entanglement. And basically, we just need to count number of these Bell pairs, Bell states, actually. So this is basically, but we wanted to be more precise. And the amount of quantum entanglement is measured, the quantity called entanglement entropy. So this is entropy, but this measures amount of quantum entanglement. And let me give some definition. And actually, in the end, this quantity is also equivalent to understand just counting number of EPR pairs. This is a basic theorem known in quantum information theory. I cannot, unfortunately, I don't have enough time to explain this. But basically, you can think we just count number of EPR pairs in a clever way. But here it's an equivalent description, but it looks so different. It's more more kind of mathematical calculation. So it's like we can decompose Hilbert space into two parts because we talk about two spins, right? But now it's about lots of spins, but we can anyway always divide spins into two groups, A groups and B groups, H8, and then Hilbert space is factorized like this. And we introduced the reduced density matrix so we started some pure state, some wave function, quantum state, total quantum state, and we trace out some part, right? Because observer is sitting A, so observer don't access B. So we trace out. We lose some information by this process, and the lost information is measured by this previous, like counting number of microsets, namely von Neumann entropy. So if tracing out B don't lose any information, this is still zero, right? Nothing is lost. But actually, in general, once we trace out pure state, we get a mixed state. That mixed state means we lost some information. So we just get some classical correlation. So that means we have some entanglement entropy. And this is also, as I told you, so it's counting number of EPR pairs in clever way. And anyway, this is a basic formula. So we encounter again this von Neumann entropy. But here it's some more advanced definition of this so-called reduced density matrix, reduced density matrix for A. And if we have some non-trivial entanglement between A and B, then this is always non-vanishing. So this is actually proportional to the number of EPR pairs. So that means that this is proportional to the strength of quantum entanglement. So this is the main quantity which we work with. So you can think of the simplest example. This is just same as previous one. This is just direct product state. That case, it's after diagonalization, this low A reduced matrix actually pure, right? Only 1, 0 eigenvalues. But if we talk about this EPR pair, Bell states, entangled state, then after the diagonalization, 1/2, 1/2. That means quite a mix. That means we have log 2 entropy. Right? Low log 2. Low log rho gives, trace low log rho gives log 2. Right? It's like just single state, these mixes. So it is obvious. But we wanted to do this calculation in more complicated situation like this. So we can define entanglement entropy, geometrical, I just call EE for entanglement entropy. So we can define this quantity in geometrical way. And the quantum manifold systems, a lot of spins, right? A lot of spins. But anyway, we can just divide into two groups, A group and B group. You can, definition of A and B, is like, definition of A is you can choose as you, right? It's infinitely many different choices if you have infinitely many spins. And if we take especially continuum limit that there are infinitely many spins, and then we have some, and if we have appropriate Hamiltonian, then we get quantum field theory, like critical Ising model at critical point, Sommers-Bars Ising at critical point, then we get, for example, Mayer-Narrow fermion theory, that's quantum field theory, like this. And still we can talk about decomposition A and B, and separation of A and B. Once you specify the region A, right, and boundary of region A, then we have factorization of Hilbert space. So here we assume time slice, right? Time direction fixed. Then Hilbert space is expressed by spatial time slice. So that we just decompose time slice into two parts, A and B, that gives a factorization of Hilbert space. And in condensed matter theory, also entanglement entropy plays a very important role as a quantum model parameter. parameter, for example, to detect some topological order and so on. But I'm not going to details of this. I'm more interested in gravitational physics in this colloquium. Okay, so these are, anyway, so we can use this definition of entanglement entropy in a quantum memory system and quantum field theory. That's what we're going to work on. And that case, for quantum memory system, especially the case we have some continuum limit. So we have a very nice property called area law. This is the area law. This is different from area law in black hole, Bekenstein-Hawking, but in the end they are closely related. That will come back. But this is found by these people. And the entanglement entropy quantum field theory includes UV divergences because here it's finite, right? This is finite because it's just two states, just only two spins. But here we have an infinite spin. Then degree of freedom is gets increasing in a divergent. So in the end, we end up with a divergent contribution to the entanglement entropy. So leading contribution of entanglement entropy in ground state of D plus one dimensional quantum field theory with UV fixed point. This is some technical assumption that at the UV we have a conformal invariance. But this is many theory belongs to this class. And so this behaves like following form. So it's like proportional to the area of this boundary, not the volume again. So the only proportional to the boundary and some cutoff constant. Epsilon is the UV cutoff constant. So this is here also, I introduced also here. And it's a UV cutoff. And it's divergent, but it's irregular, it's finite, and always proportional area. So the main reason why we have area is because entanglement is strongest along this boundary, right? So it's a middle point and the middle outside point, the far away point is less entangled. But the most strong entanglement, you can see this boundary, right? Because we are talking about entanglement with the A and outside. So this is the main reason, but there are many other technical assumptions to have this formula. But anyway, this area law is a very fundamental rule in quantum, entanglement entropy in quantum physics. So that, but here we come to the intuitive understanding of this entanglement entropy. So we have some region A and region B, and we trace out region B. So our observer is sitting outside, it's namely A region, and they cannot access B. That case, somehow, maybe observer sees something like regard, maybe this B is much like a black hole, right? Because we cannot probe inside the black hole. Very naive argument. So it's quite, not so surprising. Someone might, guess maybe this entropy, this entanglement entropy also measures the amount of lost information, maybe somehow related to black hole entropy. However, there's so area law of entanglement entropy also resembles. This also looks like very similar to the Bekenstein-Hawking formula. But however, very serious discrepancy that we cannot identify them so simply because entanglement entropy is also divergent, but the black hole entropy is finite. And also entanglement entropy here or here, it depends on the number of matter fields, somehow matter, depends on the matter. But the black hole Bekenstein-Hawking formula is just given by area divided by Newton constant. It's quite universal and nothing related to matter, existence of matter. Of course, matter back reacts to geometry, but it's not proportional to the number of matter fields. So, but still, so this naive guess doesn't work, but still it is quite natural, interesting to ask somehow, can this entanglement entropy be somehow related to gravitational entropy, some entropy which happens in gravity, much like black hole or maybe generalization? And the answer is yes. But this is possible if we use holography, idea of holography. Namely, that if we change a different dimension, a higher dimension in gravity is related to lower dimension in quantum measurable system. If we use this idea, they are directly related. That's what I would like to explain just soon. So to explain this, now I move from quantum mechanics to again go back to black holes, but maybe in string theory viewpoint. So first thing, so how can we understand black hole in string theory? Right? So we want some microscopic understanding of black holes by using string theory. Then in string theory, so anyway, black hole is a very heavy object. So we want some heavy material, right, in string theory. And good candidate of heavy object in string theory is called D-branes. I'm not going to explain D-branes, but this is basically some object where this open string can end. But anyway, so if you have a lot of D-branes, there are a lot of strings attached. There's such an object, very heavy object. And so always D-brane comes with strings, and there's a lot of open strings. And indeed, actually, if we magnify a black hole by using string theory, you can see a lot of D-branes and a lot of open strings. And this a seminal work by Strominger and Buffer quite long ago. And they show that indeed by counting number of open strings configurations, microstate, and then you can explain black hole, some class of black hole, especially extremal black holes, supersymmetric black holes. So that way, so string theory somehow, at least partially, gives some understanding of the microscopic picture of black holes. So we're gonna to use this idea, and we wanna to expand this idea. So this is but at the same time, I want to, even without string theory, we have some interesting viewpoint about gravitational physics in terms of quantum mechanical microscopic viewpoint. This is a holography. And so as we already see, so black hole entropy formula is area divided by Hodge-Newton. So why area, proportion area is mystery. But anyway, if we take this seriously, anyway, we just assume this formula. This says that if we talk about degree of freedom in gravity, this is very mysterious theory. Gravity is very mysterious theory. So degree of freedom of gravity, actually not proportion to volume, but area. So this, anyway, this formula suggests this counting of the degree of freedom. And as proposed by Tofuta and Susskind, so this interpretation actually gives, in the end, expanded into the idea of holography. Namely, if we have some gravity on some manifold, some spacetime n, and this might be equivalent to some quantum theory without any gravity, this quantum matter theory, of which lives on the boundary of this gravity. So it's one dimension lower. But this is nicely explained why this area appeared here. So because black hole entropy is area, but in terms of one dimension lower language, it becomes like it looks like a volume, right? It's one dimension lower, the area becomes volume. So it's much like thermodynamic entropy. So here we can understand black hole entropy as some thermal entropy, thermodynamics. So here it's like a mysterious gravity, but there might be equivalent. So this is the idea of holography. Of course, this is very abstract and very heuristic idea. So if we wanted to really use this idea, we first need to convince this idea, and that requires some concrete example, calculable example. And that is the AdS CFT correspondence. And string theory provides the basic framework, a basic example, explicit example, where this idea of holography works. This is first found by Juan Maldacena, and more than 20 years ago. And so this AdS CFT is basically the equivalence between two different theories. One is gravity and one is another non-gravitational theory, as and gravity is basically come from string theory, is D+1 dimensional anti-de Sitter space. And so let's take a D+1 dimension. One is maybe time direction, and D is space dimension. And anti-de Sitter space is a space-time with negative cosmological constant. And that gives some, in a particular classical limit, if we take some effective theory, we have some general relativity with negative cosmological constant. On the other hand, this theory in AdS CFT means conformal field theory. I think Suniel gave a colloquium last time, so I think you are familiar with this idea. But basically, conformal field theory is basically which lives on one dimension lower, as in holography, d-dimensional Minkowski spacetime. But this is basically, you can roughly think of this as a massless theory, some theory of particle physics, like some particle which is massless particle, like Maxwell theory or something like this, some generalization of that, like QCD and so on. And so, but here we have some, of course, coupling constant. Coupling constant, and we take a very strong coupling constant. And also we assume some large n, that means we have a infinitely many degree of freedom. Like, so if we use some language of gauge theories, we just increase the number of rank of gauge group UN, and we take n goes to infinity. But anyway, large degree of freedom and strongly coupled limit. If we take that limit, this is precisely correspond to this general relativity limit. It's a low energy limit. That means the AdS universe, this space-time gets much larger, very large scale, so that stringy effect, string excitations, you can actually somehow neglect it. So that's general relativity treatment justified for strongly interacting. So this is a quite useful tool at the same time to understand strongly coupled physics, like even condensed matter or nuclear physics and so on. That there are many works which apply where this is a kind of called applied AdS CFT. People apply AdS CFT to understand strongly coupled physics by using relativity calculation, some gravity calculation. But anyway, so the basic principle of this equivalence, you can say just they are both partition functions are equal to each other. Or free energy, also entropy, the same, temperature also same. Black hole temperature, same as thermal temperature here. And that. This is a basic bulk to boundary relation. So these are here a sketch how the originally AdS CFT is derived. This is come from string theory. So it's come from this D-branes. Again, we D-branes because D-branes are very heavy objects, and that back reacts geometry following this general relativity Einstein equation. So we have a lot of D-branes actually, but it's now D-branes as a kind of brain, like seeds, right? Extended object, not a particle. So there's a lot of D-branes, a lot of open strings, and the open string actually gives gauge theory because there are many D-branes, and each different point you can connected by open string. So there are n D-branes and n times n possibilities, and n times that gives n times n matrix. So this is a matrix valued field theory. That means UN gauge theory here. And this is because this is a heavy object in a gravity language. They back react quite a lot, and in the end encounter this space, AdS anti-De Sitter space, which I just introduced. So this is just naturally come from back reaction D-branes. And then once we go to D-brane, once we go to AdS, then D-brane disappears, only we have closed string. So theory of gravity, completely. But they are actually origin from the same one, just to come from D-brane, so they are equivalent. So this equivalence is basically the origin of AdS CFT, the reason why we believe AdS CFT. And this gauge theory is turned out to be massless, and it's conformal invariant, that means conformal field theory. But anyway, so this anti-De Sitter space looks like this metric, right? It's given by this metric, R is the AdS radius size of AdS, and the Z is the extra dimension. This is very important, extra dimension. And just we have a Minkowski space. So Minkowski space time is a fiber over Z direction. This is called extra dimension. And also important fact is that there are factor 1 over Z square. So at Z equals 0, the volume diverges. This seat, the volume of this seat gets divergent. This divergent, this is a classical divergent, geometrical divergent, actually in AdS CFT equivalent to quantum mechanical divergence, namely UV divergent. UV divergent of quantum field theory is just equivalent. So there's a huge degree of freedom here. And if we go to the large Z, we have an infrared degree of freedom. Z is basically proportional to the degree of freedom of the energy scale at Z. Z is a length scale, basically. And we have thermodynamics here and equivalent to, so thermodynamics of black holes equivalent to thermodynamics of this gauge fields like materials, and they are equivalent. So this is how AdS CFT works. Okay, so now I come to the my contribution of this subject, namely is how we apply this idea of holography to calculate entanglement entropy, because we want to, original motivation, one motivation is to relate entanglement entropy to black hole entropy or gravitational entropy. So this is my work based on the Shinsei Ryu and also Fubeni and Rangamani. And so this entanglement, so we already defined entanglement entropy, right? Just basically measure the amount of quantum entanglement with A and B. And here we have some AdS CFT picture. So this bulk is here, this is anti-De Sitter space, and this is a boundary, right? Here it's AdS boundary. So boundary where we CFT, the CFT lives on the boundary. So we cut the space into two parts as usual, A and B. Then we define entanglement for A. And to calculate entanglement entropy in CFT, conformal field theory, some quantum field theory, we just extend this boundary towards the bulk, right? We extend. So we have some this codimension 2 surface in the bulk. So this is this boundary we call gamma A, but there are infinitely many different choices of this surface, right? We just require this boundary, this surface end on the boundary of A, right? So even in the bulk, they separate two regions, but we minimize the area. This is important, this minimization. This is actually equivalent to somehow solving Einstein equation, but as we minimize the area, then we have some unique definition of the surface called gamma A, and we just calculate gamma A, area of gamma A, and divided by 4 Newton. This is exactly the same formula, which happens for Bekenstein-Hawking formula, actually. But actually, this is more general in that this surface is no longer, not always horizon. I'll come to this point. So this formula actually calculates this boundary CFT entanglement entropy. And so we can check this formula, the many examples, that's what we did. Also, later, by Lukoito and Maracena, this formula also proven, derived in the context of this bulk boundary correspondence. It's here, just equivalence partition function. And also, because I'm giving talk here, so I'd like to also emphasize that actually, so here we have this formula is for static, actually true only for static space-time. And if we think about some time-dependent case, we should use this time-dependent version. It's called covariant entanglement entropy. And then we are not looking at the minimal surface, but extremal surface. And this formula is found with Veronica Fubeni and Mukund Rangamani. Actually, when we met in Puri and in the Indian Strings meeting 2006, and it's a quite really, this project is really initiated in India. At that time, this is a picture at that time. So myself and Mukund and Veronica and Shiraz also there, and Marti. It's a really great memory for me. And so then also I'd like to give some intuitive understanding. I'm not going to anyway technical derivation and so on, of course. So I just want to give some intuitive understanding of this formula. It's actually based on very highly motivated by black hole entropy. And so we have this setup. This is a boundary of AdS, and we have an observer sitting A, and observer C this gamma A. And then inside gamma is somehow hidden because this is region B, right? This region B, the observer cannot access. So that means there are some hidden region, much like black hole interior, that which hides information from this observer, right? So observer sees some black hole-like horizon, and this is precisely the gamma A, which I mentioned. And so the reason why we minimize gamma A, so we just want to optimize this very naive idea. So this is, one motivation why we originally proposed this formula. But of course, we checked this many different examples. And anyway, so that case, this you can regard this as a kind of generalization of black hole entropy. And inside this region, this white region, which the observer can access, the bulk region where observer can see, is called entanglement, which this plays a very important role in recent development of string theory. And so I'd like to also mention some precise connection to black hole entropy. So we have a black hole here. We have a black hole. And so this is anti-Doshita space outside, and we have boundary. So we can talk about that case if region A and region B. But black hole gives some topological abstraction, especially I'm talking about the eternal black hole, mixed state black hole. So we can think about two different geodesics, two different minimal surfaces, gamma A here, gamma B, right, which covers B and which covers B, A. So they are different. And if we compute SA, we should use this gamma A surface. If you compute SB, then you should use this surface. And they are different. They are different. And especially, and this is quite well known. So for mixed state, SA is not equal to SB, but for pure state, they are equal. Because indeed, obstruction of memory black hole disappear, right, for pure state. So that case, they are same surface, consistent with well-known result in quantum information theory. And now we take a total space A is a total space. We just shrink the B to 0 size. That case, this A covers whole space. And still, but as you can imagine, we have something remain, this minimal surface, which precisely coincides with black hole horizon. And that case, this entanglement entropy for total system is precisely same as thermodynamical entropy, thermal entropy. So that's a connection to thermal entropy and entanglement entropy also. Connection. This is equivalent to just black hole entropy. So black hole entropy, you can see this black hole entropy is a kind of special case of this holographic calculation of this entanglement entropy. I just call it HE. Okay, so this formula also gives a quick derivation of this what is well known and very important inequality in quantum information theory, namely strong subrelativity. They are summarized into two inequalities like this, but we can quickly derive this because we have A, B, C as the boundary. So this red surface covers AB. So this compute SAB, right? This area is SAB. Area of this blue guy, BC, is SBC. But we can decompose this way. Total sum is the same. But actually, if we wanna get some surface for ABC, right? Then there are smooth surface. This is not smooth, right? This is a cusp, and this has a smaller area, obviously. And also for B, there are smaller area surface. That immediately prove this inequality. And another one, if we choose different recombination. So that way, somehow, this is the essence of AdSFT, that algebraic property of quantum information theory or quantum mechanical system actually turns out into very simple geometrical property. So like this is triangle inequality, right? Geometry. It corresponds to very non-trivial, very complicated algebraic inequality. Indeed, this takes some time. I mean, if we want to prove this formula in quantum information theory, but actually it gives some simple geometrical interpretation. This is also, power of this holography. And these are more details, but if we wanted to see some express calculations, so you can do this especially. And so we can calculate like this. And so we find some area law divergence. Leading term is area law divergence. And it's a lot of screen. So you can take any shape. And at least if we use some numerical calculation, we can always calculate this minimal area numerically. And then we get always this kind of expansion. And also we can look at we can find some conformal anomaly for even dimension, and also some quantity, some analogous quantity called F quantity for auto dimensional case. But these are anyway for just experts for quantum field theorists. But anyway, we start with area law divergence. It's consistent with what we know for the general behavior of quantum fields, as I mentioned. And now also I'd like to also comment that, so anyway, in gravity, Einstein equation is a very basic equation of which describe the dynamics. What about Einstein? How can we understand Einstein equation from quantum entanglement? So in quantum entanglement entropy, so we can show this very interesting relation called first law. It's a kind of analogous statement of first law of thermodynamics. It's a kind of generalization of first law of thermodynamics. And this means that basically entanglement entropy increase how much is the growth of entanglement entropy equal to growth of energy, some energy, but more precisely it's called modular energy or modular Hamiltonian, defined this way. And basically it's energy and energy, right? Delta TdS equal to TE, that E is energy. This is the first law, right? This is basically the same form, takes the same form. And that actually turns out to be equivalent to Einstein equation at the leading order of perturbation. Not exactly full Einstein equation, but the leading of Einstein equation. So first of all, you can rewrite this in terms of this partial differential equation. And so this increasement entanglement entropy, and we specify subsystem, right? So the center of mass of subsystem is T and X, time and space, and size of subsystem also important L, right? That gives L also here, some derivative L, somehow time derivative gone. But anyway, this is much like actually De Sitter space instead of anti-De Sitter space, but somehow because of some nice symmetry, conformal symmetry. But anyway, this second order differential equation, we can understand this as actually equivalent to the Einstein curvature term of this Einstein equation, left-hand side of Einstein equation. And this, if we have some matter, so we get a matter contribution. So this gives Einstein equation. But it's in perturbative sense. And this first law of entanglement entropy explains that way perturbative. And higher order perturbation also, there are some developments these days. So this is the Einstein equation, how we understand the Einstein equation from quantum entanglement. Okay. So now I would like to go to the final topic of this talk. And this is how we understand the emergent space, right? Emergent space-time or universe from quantum entanglement. And entanglement, holographic entanglement entropy suggests that there is a one qubit entanglement, one EPR pair for each one Bell pair for each Planck length area, right? So this is just again, I write this holographic entanglement entropy calculation. This is a boundary where CFT lives. We have a region A and region B, and this is a gamma A surface, right? And if we take a Planck unit cell, so one Planck unit cell has a one Bell pair. So like this, written this, like bars, right? Written in this bond. If we pick up one small bond, then this looks like actually mini universe, like Planck scale universe. If we just only have one EPR pair, so because entanglement entropy is just order 1, log 2, right? Order 1. That means entanglement entropy is, if we rewrite in terms of area, it's like a Planck unit area. So cross-section Planck unit area, that means, of course, microscopic unit. But actually, so this macroscopic anti-De Sitter space, we can regard intuitively at least, so we can, as a correction of such a EPR pair, some mini universe. So here is the important point is that we can change the location of A and B, size of A and so on. It's like as much you like, right? Even though this is a picture of a particular sketch of particular choice of gamma A, but you can choose many different, gamma A. So that means this EPR pair is everywhere in the space-time. So this suggests the very heuristic argument, very intuitive, but it just suggests that gravitational space may consist of Bell pairs, like some entanglement. So indeed, this holography, if we use holography as a microscope, so we magnify the region and we see some EPR pairs. This is a main point of this Colloquium, but of course we wanted to make this more precise. And first thing we can do is to find some easier model, like toy model. And that is actually provided by a nice framework called Tensor Network. Tensor Network is developed originally in condensed matter physics, or its connection to quantum information theory. That basically very practical motivation. We want to somehow solve very complicated Hamiltonian in somehow numerically, but in a very efficient, using efficient algorithm. So this and Tensor Network, we want to find some. We started very complicated Hamiltonian. We want to find ground state, and we use some variational principle. In that case, we need a good, very nice ansatz of variational wave function, right? And the Tensor Network provides that in a graphical way. So it's graphical description of quantum states, and it basically consists of network of quantum entanglement. So you have graph which basically describes quantum entanglement, and there are many different kinds of tensor network. I just pick up a very beautiful one called MERA, multi-scale entanglement minimization ansatz, found by first constructed by Geoffrey Vidal. This is because this is tensor network suitable for conformal field theory, quantum critical point. So the conjecture, which argued by Brian Singer, is that. So it's related to this emergent space-time. So it's like conjecture is if we take an anti-De Sitter space and if we take a time slice so that we define some quantum state, right? State is at some particular time. Actually, this much looks like a tensor network. Maybe tensor network gives an explanation of AdS CFT correspondence. So indeed, this is very similar. It looks looking indeed. So this is here is a sketch of a mirror, right? So we start. So here we have some mirror, and so we have some layer. We start with a UV layer, and here we expect some microscopic wave functions realized here. But under like renormalization group flow, we coarse-grain, right? And two spin to one, combine into two, and we repeat it. And in Entropy is just a single spin. And that way we construct wave function, fine-grained construction by adding a number of spins, or in other words, adding links, right? Links, this unitary transformation and this isometry, they're basically unitary transformation, which adds entanglement. So we start with single spin, add a lot of entanglement of spins, and realize a final ground state of some given Hamiltonian, some CFT Hamiltonian. So this is the idea of meta. And this step looks like, of course, this looks like real space renormalization group flow, but this looks like anti-De Sitter space because this geometry is really looks like this, right? It's like evolving, right, in spatial direction. And if we naturally define metric here, then we just get the anti-De Sitter metric. So here, if we have round version meta, the boundary, we realize some quantum state. We wanted to find some fine-grained ground state of some given Hamiltonian quantum conformal field theory. And that case, we started just single state and expand by adding entanglement. And this much looks like anti-De Sitter space, right? This famous picture. So this each of these black parts is evil and angels, and they're same area. And if we count number of entanglement entropy, so we can talk about region A and region B, right? Then we can estimate entanglement entropy just counting number of bonds, right, which connect these two regions. And we minimize it because if we go this way, it's like overcounting entanglement. So if we optimize counting, then we immediately leads to the idea of minimal surface and precisely agree with this holographic entanglement entropy. Right? It's also this minimal area. So that way we have a nice analogy between them. And zeroth order approximation, this should work. So this is a very promising action. And also we can, more generally, we can say that if you have a tensor network, we can cut out any orbital region, sigma, and then we can associate. Tensor network allows us to associate some particular unique quantum state. And this is called, we call this a surface state correspondence. So if you have some gravity, this is also true. We expect this is true also gravitational theory. If you have gravity and take some codimension to space, codimension to surface, then we can associate one quantum state. And this also gives this entanglement entropy connection and so on. So we have some direct correspondence between some geometry and quantum state by this surface state correspondence. This is this should be true if this conjecture is true. Okay, but here is a kind of here we are talking about. We talked about some toy model. So now I'd like to give a more sophisticated model so that it fits nicely with quantum field theory. So usually in string theory and AdS CFT, usually we formulate anti-De Sitter space. Continuous AdS spacetime is dual to continuous quantum field theory. And we want to describe CFT as a, that means we should, this tensor network is quite discrete spin system, so we need some continuous description. So for that, we would like to take advantage of path integral. And this leads to the idea of path integral optimization, which I developed with many people, including Alpan. And so the idea is we started some Euclidean path integral. As you know, Euclidean path integral defines quantum state, right? Like Hartree-Hawking prescription. So if we take a Euclidean path integral for infinitely long Euclidean time, then you just go to the ground state. Right? You get a ground state of a function, which projects down to ground state. Hamiltonian evolution projects down to ground state. And anyway, that way we can describe some quantum state by Euclidean path integral. But if you have some, especially in the case of conformal invariance, you can have infinitely many different ways to realize same state by Euclidean path integral, by changing background. So among them, we just want to minimize computational costs of, actually we have in mind some discretized version path integral, but anyway, we want to minimize computational costs of path integral to obtain some target space, like ground state of conformal field theory or excited state of conformal field theory. Some given state, there are a lot of different path integral give the same state, this given state, but we just want to pick up minimum, right? Because just reduce the computational cost. If we imagine, if we do this path integral on computer, right? So we discretize into lattices. And so we, after some thought, it is quite natural, we get to this idea. So we can actually coarse grain quite a lot initially, because this is an infinitely long time path integral. So short wavelength structure is not important. It's just decay later time. So initially we can coarse grain a lot, a little bit, gradually we fine grain the mesh, right? Lattice structure. And end up it's quite fine grained lattice. And this much looks like, mirror, like tensor network, right? It's very similar, looks like very similar to tensor network. And also, at the same time, this reproduces time slice of anti-Doshita space. This metric obviously looks like hyperbolic space. This is time slice of anti-Doshita space. And we want to make this more somehow precise by using equations, sophisticated equations. So for that, we have to rewrite this geometrical picture of we change the cutoff. That is constant. Cutoff scale locally. This is the point of this idea. This is a uniform cutoff, right? But here we coarse grain and here we fine grain. That way locally we change the cutoff. So we describe this local change of UV cutoff in terms of metric by changing metric. So we take a rule that the whole some unit area we have just one cutoff, right? One lattice for one unit area, and that means we have a lot of fine grain, meaning you have a larger value of metric. Then we have a lot of cutoff. A lot of lattice points, but a smaller metric means we have a less lattice points. So we have in 2D, right? We focus on 2D CFT. So that case we can use. We know that it's like always metric looks like this while transformed form. So we have only non-trivial degree of freedom, just first this coefficient, right? Exponential to omega. Omega is basically a wild factor. It's a metric. If omega large, that means that we are very fine graining. Omega very small, that means we are coarse grain. So that way, but owing to conformal symmetry, we are talking conformal field theory. So actually, wave function is invariant under conformal invariance. But if we care about the normalization changes. Partition function, normalization partition function changes. Equal. So we like this normalization is we call exponential CW. And these two wave functions both describe same state, right? Because normalization wave function is not usually not important. Right? It's just both are describe ground state of some, for example, some conformal field theory. But this normalization depends on this omega. But normalization actually is important if we imagine some numerical calculation. In the end, we have to. If you repeat the same calculation many times, you get a lot of large value of normalization. So this is a kind of repetition of the same procedure, right? Measure of repetitions. So this is the C is basically computational cost. And also recently this is called computational complexity. One definition of computational complexity. And then we can actually, and in 2D CFT, we have a very beautiful story. And this C omega is given by mathematically beautiful formula, namely Liouville action. And indeed, if you minimize this Liouville action, then immediately we see the AdS metric, time slice AdS, that hyperbolic space metric. It's very easy to show. So that way, we have this, we can justify this picture by explicit calculation. Okay. And so if we talk about the excited state, then we put some local excitation. This gives an energetic source. And to optimize path integral, actually, but if we coarse grain quite a lot here, then we lose information of this excitation. We actually, after calculation of this similar to this one, we end up with the, we know that we have to fine grain metric here. And that exactly is very similar to the situation in general relativity. So if you have an energetic source, that changes the local geometry, right? Back-react geometry. And here we have an energetic source or information source. Then information source changes the background geometry. So it's a very parallel with general relativity idea. Okay, so finally, so I just want to quickly mention that another quantity, but it's also already appeared in my this optimization, complexity. This is also a kind of counterpart or some correspondence between some quantum information quantity to AdS-CFT, like entanglement entropy, but it's an independent quantity other than entanglement entropy. And this computational complexity basically measures how much a given state is complicated compared with some given reference state, which is we take the very simple state, just all upspin state, no entanglement at all. So how that is precisely defined how many quantum gates you need, quantum unitary transformation you need to find this state, some given target state. How many gates you need to create this state, right? This minimum number of gates. And this is called complexity, and there are many interesting developments these days of how to define complexity in quantum field theory, especially this works, and also very important consequence of the whole remuneration group flow done by Alpan and collaborators. And also at the same time, there are nice holographic counterpart is conjectured by Susskind and collaborators. And sometimes there are two possibilities, like for example, volume of some time slice. Entropy is related to area, but it's here it's a volume, or some gravitational action in this region called Wheeler-DeWitt patch, and so on. There are many interesting progresses these days. And then here's a summary of correspondence. It's just previous point. Complexity development says that codimension one surface in space-time is related to area volume of codimension surface complexity, and also in other words, this also related to surface state correspondence I mentioned. This evolution of this codimension one space is correspond to tensor network itself. Right? And if we talk about codimension two surface sigma, then this is related to quantum states based on this surface state correspondence or intuition from tensor network picture. And if we calculate the area of codimension two surface, it gives entropy. Sometimes black hole entropy, and sometimes entanglement entropy, and sometimes more general quantity. And finally, this means that geometry of space-time, we can understand it's a geometry of quantum entanglement and dynamics of gravity. We can regard it as an evolution of quantum entanglement. Okay, so these are basically all of my talk, and just summarize conclusions. So we're starting from black holes and quantum entanglement. We reviewed recent progress of deep connection with gravity and quantum information. And holography related to different theory, gravity and field theory of quantum matter. And if we look this way, so at least we emphasize that, so if we view gravity from field theory, so we have some emergent space-time or universe from quantum entanglement. But we can become more ambitious that we can go opposite direction. And you may view some gravity is kind of, so here, this is quantum computing and such, very recently highly developed, also including an experiment. And maybe gravity might give some idea of fastest quantum computer because its gravity is strongly coupled. And there are also conjectures. Black hole gives the fastest conjecture like Sesloid, and it's AdS-CFT might realize. Because AdS-CFT gives a very efficient calculation of strongly coupled physics. It's almost impossible for classical computer. And I mean, it's somehow, it's a very surprising thing happens. And finally, so this connection also, there are very interesting recent topic, like it's a black hole, about black hole information paradox, which this is based on this called island conjecture. This is a kind of generalization for holographic entanglement entropy, how to compute entanglement entropy in the presence of gravity. And this, so that gives some nice resolution of some paradox of black hole information. Black hole. But still, this black hole issue is developing. As I wrote here, it's a microscopic origin of black hole, especially from gravity viewpoint, cross-link viewpoint still developing. It's not, there are no complete, it's also sometimes called edge mode of gravity, but it's not completely understood. It's quite important future problems. And also AdS-CFT itself is kind of black box. We confirm this in many ways, but it's still, we are lacking explicit proof. So might be this quantum information approach is maybe helpful and give some explicit proof of this. And after we understand AdS-CFT, we want to generalize AdS-CFT to more general spacetime and more realistic spacetime in terms of cosmological spacetime, or like digital space or big bang singularity and so on. In the end, we want to understand the origin of this our universe by using quantum gravity. Okay, thank you very much. I think I'll stop here.